that it's okay, can submit it after class. I think I only saw 3 or 4 submissions. Okay, so we had 3 problems, right? So we had, I think one problem was, most of you did the first one, right? So homework problem number 1, what was it? So it was, I was asked you to write down the generating function, right? So remember, we had so we have this notion of generating functions. Which is what? It's a function that it's a function of some formal variable, right? Let's call it z or x, right, or t. And the coefficients of this function, they give you some information, right? So coefficients in front of the powers of some of this formal variable. So in other words, it's a convenient way to package the information into the into one function, right? So that's the whole meaning of the generating function. So first the question was write down the generating function for all distinct partitions, and then it's let's call it p. Well, let's call it so p distinct of z, right? And then p odd of z. So we have proven combinatorially without any algebra on the very first lesson that these two are the same. So in other words, for every n, the number of distinct partitions matches the number of odd partitions. So now let's prove it using the partition functions. So who wants to tell what's the partition function for distinct partitions? Michael, yeah, please.
It's 1 plus x times 1 plus x squared times 1 plus x third and so on.
Can you explain why? Well, I call it z here. Okay, so what's the why is this the product of this parentheses like this?
Because it's like each like one only has one of its like coefficients.
That's right. Yeah. So like by construction, right? We see that every coefficient. So there is only one in the resulting product. There will be only one term with its unique power, right? So in other words, it will only count those partitions like the part. So you need to do the expansion would be some some coefficients Cn. Well, when after you expand the parentheses, right, it will be infinite sum like this Cn z to the L, right, and then this L would be K1 plus K2 plus K3 plus and so on. And then because the function is presented in this way, we are guaranteed that all of those K's will be distinct, right? So all of those parts will be different because they come from different powers of z, and then the fact to have plus signs also takes care of that. Okay, so this is p distinct. Okay, now what about p odd? Kyle, please.
1 over 1 minus z times 1 over 1 minus z cubed times 1 over 1 minus z to the 5th, and then on and on.
So like this, right?
Yeah.
Okay, explain why.
Well, it's like the generating function for normal partitions, except in this case, you're only given the option of choosing between odd numbers and no even numbers.
Exactly. So remember that for normal partition, you would just put any power there, right? So not z to an odd number, but z to any number, including even numbers. But here, since we restrict ourselves to odds, right? So that's how it works. That's how it plays out. Yeah. So indeed, so those generate odd partitions. Okay, and now, so those two look a bit different, right? So can we prove that they're actually the same? What's the kind of fastest way to show that these are in fact the same functions?
The way I did it for the homework, I did like 1 plus x times 1 plus x squared using the distinct function formula. And then I took 1 minus x squared divided by 1 minus x times 1 minus x to the fourth divided by 1 minus x squared. So you're taking the full expansion of the distinct and then dividing it by the odd, and then you get them equal to each other. Because once you divide 1 minus x squared divided by 1 minus x times 1 minus x to the fourth divided by 1 minus x squared times 1 minus x to the sixth divided by 1 minus x cubed, you would generate a function for odd. So using distinct and then dividing, you'll
Yeah, so divide. Okay, so do you want to write the p odd first in a different way, or just divide p odd or by p distinct? So these are the functions, right? So yeah, so with this now you just divide them or what? Can you repeat again the first sentence, right? So what do you want to do first?
You could do odd divided by distinct. I just did distinct first, but
Okay, sure. Let's okay. So right, so distinct is written over here. What do you want to do about it? So you want to do represent say 1 plus yeah, sorry, can you explain that again? No.
can I like show what I did on my paper?
Yeah, sure.
Okay. So I used the distinct over here and then
Oh, okay, yeah, good, right. So yeah, so in other words, you're saying yes, p distinct of z. So the trick was to write this as the yeah, so 1 minus z. So it's 1 minus z squared over 1 minus z, right? So times 1 minus z to the fourth times 1 like this, right?
yes.
Right. So you use it and then times 1 minus z to the sixth divided by 1 minus z cube.
And then when you simplify all of that, you'll get the generating function for the odd partitions.
Yeah, so because here so this is the same as it's the it's a product of 1 minus z to the 2k divided by 1 minus z to the power k, right? Yeah, and then yes, k goes from 1 to infinity, and so on. So right, and then the and then this you can write as right, so like this. It's so let's just look at the thing here. So you can write it as 1 minus z to the k, right? Parenthesis open, 1 plus z. I'm sorry, I think what they want to do now, so they want to divide by 1 minus z to the k. So you want to have this as the geometric sum, right? Or what?
Yes.
Yeah. So right. So what the?
So what I did was I simplified like 1 minus z squared over 1 minus z, and then that gives you like once you change all of the powers, so like 1 minus z to the fourth over 1 minus z squared, you divide those two, and then 1 minus z to the sixth over 1 minus z cubed would give you z cubed, and then that would give you the odd function.
Right. Okay. So, sorry. So you cancel them. Not everyone. Okay, right. We just I just write down some. Yeah, it's pretty right. So 1 minus z to the 8, 1 minus z to the 4. Okay, and now we can cancel some of them, right? Right. So it cancels like this, right? And this cancels like that, and then you can show that all even guys cancel, right? Yeah, that's right.
Right, so you're left with the odd ones.
Right. So, okay, so let's write on more. So it's 1 minus z to the 10, z to the 5. So see here on top we only have even powers, and on the bottom we have all powers, right? So therefore even powers cancel out. Then we end up having what we want, right? We end up having only odd powers, right? Which is equal to p odd. Good. Yeah, I think other solutions were similar. Do you agree? Any questions? So Eunice, is it square or is it? Yeah. Okay. Good. Okay. So now the next problem, which was a little bit more complicated, I think, the number 2, about prime decomposition, right? So we had this. So we need to prove that sum of 1 over n to the s when n goes from 1 to infinity, which some of you mentioned it's the Riemann Zeta function, which is this is absolutely right. But we don't need you don't need to know that this is Riemann Zeta function. So p over set of primes, right? P to the s over p to the s minus 1. Okay, what to do about this? Wants to explain. It's kind of surprising, right? That prime numbers appear in this kind of formula, right? Well, maybe not, but you did have some of you did have solutions. Just explain me a couple of them. I'm not saying that all solutions were correct, but we'll figure it out. Okay, maybe we can start together and then we'll see how. So the idea is to see that, remember I mentioned to you that although the problem itself is not about partitions, but kind of the style, like the way of solution, like the method of solution is kind of close to what we did with partitions. Okay, so how about we start with the right hand side, right? And we'll rewrite this thing, right? So p to the power s with p to the power s minus 1 is equal to, let's just invert it. Okay, and then it's equal to 1 minus 1 over p to the power s to the minus first power, right? Or if you use the geometric sum, it's equal to 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the 3s dot dot dot. Okay, so that should sound familiar, like, you know, the geometric sum we did before, we used before when we derived p of n, the function p of n. Well, now we need to consider product of those. So it's product of p in set of all primes of this right hand side is 1 plus 1 over p of s, p to the 2s, etc. Now let's collect all the terms and see what this product can be brought in, what is the way we can represent this product differently? So let's see. Yeah, so we need to multiply. Yeah, so for every prime p, we take this infinite sum and multiply them all for all prime numbers. What do we get in the end? So this is where we should see the kind of partitions playing roles.
Well, I was thinking just like with the partitions, like each actual number on the left-hand side is simply composed of a number of prime numbers multiplied together to create that particular fraction.
Mm-hmm.
So like on the right-hand side, if we have all of these primes,
well, you're talking about this equation. So left-hand side is this, and right-hand side is what we need to write. Or are you talking about the original one?
Oh, I was talking about, for the left-hand side, I was talking about 1 over n to the s, but like,
okay, okay. So you want to do it differently. You want to do it.
Well, I mean.
Okay, but okay, let's see what you want to say. Right. Okay. So yeah. So this is the. Okay. Continue.
I was going to say that just that 1 over n to the s, each part in there, like 1 over 6 can be simplified to, or well, can be factored into 1/2 times 1/3.
Yes, exactly. So right, good. So every n, right, can be factored into prime numbers, right? So every number has a prime number decomposition. Good. Now, do you see? Can we get this prime decomposition over here? So the way I wrote down this here is here, right? So we have this 1 plus 1 over prime to the s plus 1 over prime to the 2s, etc. So now let's multiply them together and let's see let's collect all the powers, right? And remember, p's are primes. So do you think you can find what I'm talking about, the prime decomposition of every n? So the idea is to get from here to here. Let's just convince ourselves that this is true. So it looks like Kyle convinced himself, but okay, so maybe give other folks maybe a minute or two to think over. So what Kyle is saying is, okay, well, n is an integer, right? And we take sum of all integers, right? Now we know that every integer has a prime number decompositions, like 6 is 2 times 3 and so on, right? Some numbers are prime, so they just stay themselves, right? So prime times 1. And here in this expression over there, we have this sum, right? So it's the product of infinite product of infinite sums, right? So we multiply all the primes and collect them together. So what gonna get? What will the sum look like after we've done this multiplication? If you are not convinced, it would make sense to do an example. So which prime numbers do we know, right? So 2, right? 2, 3, 5. So it would look like this: 1 plus 1/2 plus 1/4 plus etc. multiplied by 1 plus 1/3 plus 1/9 etc. 1 plus 1/5 plus 1/25. Okay, and then there'll be infinitely many, but let's say we only look at small fractions, right? So 1, right, plus what? What's the next? Oh, sorry. Let's order terms in right hand side in decreasing order, right? So we would multiply fractions with the smaller denominators first, and then we sort of will go and then we'll go down, right? So we expect the series to converge, so the terms will go down as we go. So we have 1, then plus what? Oh, actually, I think somehow I put s is equal to 2. I apologize. Excuse me. I shouldn't have done that. Somehow I assume that s is equal to 2. 2 to the s, 3 to the s. So s, and here it's 2s, 2s, s, 5 to the 2s, and so on. Right, so we have 1 times, there'll be 1 to the 2s plus 1 over 3 to the s, right? Now, will we have, so yes, so that comes from multiplying this series by this 1, right? But are we going to get, for example, 1 over 4 to the s? So 1 over 5 to the s is here. So we're going to get 1 over, so remember, so the idea is to get this guy. So sum of all fractions, right? 1 over n to the s, where n is every integer, right? So we get all the primes just by, looking at this thing, right? So we have, so yeah, so when you multiply, so 1 over 2 to the s times 1 is this. So we get sum of all the primes. Do you see we can how to get composite numbers?
You like multiply two values, like 1 over 2 to the s times 1 over 3 to the s, and you get 1 over 6 to the s.
Yeah, exactly. So like, yeah, so to get to 1 over 6 to the s, so all of those guys will come from, yeah, they will come from like one from here, 1 from there. So, and then as you can see, you can always find, for every integer, you can always find its sort of prime decomposition, right? So in other words, what this is equal to is that it's sum over 1 over, well, 2 to some power, say, called k2 times 3 to the power k3, 5 to the power k5, etc. So sum of all of those k's, k2, k3, k5, infinitely many of them, right? And that's exactly the thing that you want, right? So in other words, over here in the denominator, we'll get prime decomposition. We'll get prime decomposition of the number, of the number n. So the way this product is constructed is that coefficients, after we've done all the multiplication, right, an ordered term in the decreasing order, we will have prime decomposition for every. I apologize. Yeah. Oh, sorry, guys. So I need to step away for 1 second. Can you? There's something going on in the house. So good. So is this problem clear? If not, Kyle, can you explain it to the rest of folks? If not, then I'll be back in 2 minutes. I'm sorry. I'm sorry for that. Yeah. So 1 second.
Kyle, I have one question for you. When it says 1 minus 1 over p to the s to the -1 power, do you see that at the top?
Yeah.
How does that factor into 1 plus 1 over p to the s plus 1 over p to 2s?
So you remember how when we had 1 over 1 minus x, it became 1 plus x squared plus x cubed.
Yes.
Well, that's 1 minus 1 over p to the s to the -1 is basically that. It's 1 over 1 minus the quantity, 1 over p to the s. So.
Okay, got it. Thank you so much.
Yeah, I apologize. There's something they came to fix something, and you never know when the handyman comes. It's okay. So did you resolve it? Is it clear now?
Yes.
Good. Okay. And finally, And finally, the Fibonacci problem. So prove that P of n is always less than Fn, where n is the Fibonacci number. Oh, less or equal, should I say, right? Because for the first three, I think it's the same. There are many ways to do it, right? So you can either use recursive formula or Michael, please. Yep.
Well, I have a question. Like I lined up the P of n and the Fibonacci numbers, and P of n is greater than like a few of the Fibonacci numbers.
Well,
up
so
to n equals 8.
Oh, P of n. Okay, let's do the table. So P of n and Fn. So okay. So it's what 1, 2. I'm going to pull up the table. So 1, 2, 3, 5, 7, 11, 15. Right, and Fn is what? It's 1. Well, if it starts with 0, right? So it's in this case should be also Fibonacci is 1, 1, 2, but then this one, so the kind of F1 is like F0. The first one is F0. So it's I think you probably because you shift the axis here. So Fibonacci is 1, 1, 2, 3, 5, etc. But this is F0, right? So if you like P of 0, so if you denote P of 0 is also equal to 1, then you add another 1 over here. So it will be actually 1, 2, 3, 5, 8, and now it's 13, 21. Did it happen because of this reason? Because you sort of
Yeah. I lined my numbers up one to the right.
Good. Yeah. Okay. So right. Yeah. So in fact, yeah, I think it's a good convention to have P of 0 is equal to 1. Yeah, and then this first one is F0. Yeah. So this way, P of 1 is less or equal than F1. Yeah. So indeed, it seems to be working, right? And then was it 34? And here we already have 22 and so on. So why is it always the case?
I started out by writing the recurrent formula for P of n.
Okay. Yeah, so we know that the recurrent formula for every n, it gets the structure with pentagonal numbers, right? So yeah, so for example, P of n, right, is equal to P of n minus 1 plus P of n minus 2, right? So that part is the same as for Fibonacci, right? So Fn is equal to Fn minus 1 plus Fn minus 2. But as we know with Fibonacci, with partitions with P of n, there is also continuation, right? It's minus P of n minus 5 minus P of n minus 7. So remember that these guys, they always enter with minus sign, but then we get addition again. So plus P of n, what's next pentagonal number? Minus 12 plus P of n minus 15, and so on. So now, Kyle, you need to prove us that this thing is always less or equal than 0. Why is that?
Yeah. So from there, I sort of paired up the sort of like the negatives and positives. So I paired minus P of n minus 5 with P of like n minus 12, all of that. Yeah. And because P of n minus 5 is always greater than or equal to P of n minus 12, because n minus 5 is greater than n minus 12, the negative quantity is always greater than the positive quantity. So
that's right. Yeah. So indeed, so this is greater than that. This is greater than that. and so on. So indeed, so if you pair them up, you can sort of convince yourself that this tail is always non-positive, right? So it can be 0 if there are no terms, like as it happens in the beginning of the table, like in the left side of the table. But otherwise, you're going to have these corrections, which are always negative, right? And which will bring the value of the P of n down compared to Fibonacci numbers. Yeah, that's right. Yeah. So using the recurrent formula is actually the fastest way to go. Questions? Great. Okay. So for the rest of today, I think we'll continue talking about partition functions, and then we'll start talking about the asymptotics of P of n. So I told you that the P of n does not have a formula, so you cannot write P of n equals stuff, but there's almost a formula. So in fact, I mean, there's a formula that you can teach your computer to do it. So there's a series that you can write down. The series takes values not in integers, but in real numbers. And then after computing several terms of the series, depending on n, we need to compute given number of terms in the series, and then you need to approximate it to the nearest integer. So this way, so if you remember the movie that I showed you, I showed you the clip from The Man Who Knew Infinity last time, right? So Ramanujan and Hardy, they used, well, this kind of trick. So that's why they calculated so fast. They made a mistake because at that time of this dialogue, their formula was not quite correct, but later they corrected it. So by the way, did you watch the movie? Did you download it and watch it? It's called The Man Who Knew Infinity. Right. So it would be the next homework. I mean, seriously, it's a good, it's a pretty good movie, like the life story of Ramanujan. So let me sort of show you where we're going with this. So the okay, so maybe I'll start with this, and then we'll talk more about partition functions. So to prove the full formula, we'll need a little bit more analysis. So we need to know some of the complex analysis. We're not going to do it here, but I'll prove some part of the formula. Okay. So for example, okay, so we'll start today, and maybe in individual sessions, those of you who will be interested in this kind of analysis kind of thing. So I know that most of you took the AP calculus, right? So well, as you probably know, there's also calculus in complex numbers, which is called complex analysis, and there, you know, it's a bit different than it's different from real calculus in many reasons. Well, so because now complex numbers are, you should think of a complex number as a pair of two real numbers, and when you do integration on complex variables, you integrate over some path in a complex plane, and it turns out that the choice of the value of the integral when you do the integration of, so you have, maybe make one comment here. Say there's a complex plane, and then you have some function can be 0, it can be infinite at some locations, and then you can choose the integral in integration contour in a certain way. So it turns out that if the function is differentiable, if you can take derivative on this, then the value of this integral, if it's a closed path, it only depends on values of the function, or rather derivatives of the function at some fixed locations, which are called yeah. So and then so computing integrals and complex variables is much easier than the real numbers. You actually don't need to do this the Newton-Leibniz formula, right? You just write the formula, write the integral, and then you essentially can find the answer almost right away. So yeah. So that part we can leave this out for some individual sessions if you're interested in this. So let me know if you'll be interested in studying sort of this complex analysis kind of approach to this partition functions. But today we'll prove a couple a simpler formula. So first let me formulate this asymptotic partitions. asymptotic behavior of P of n. So in other words, how P of n looks like when n is large. Like, is there any sort of simpler formula or like approximate formula that gives you the answer with some precision for what is P of n? Okay, so let me write you the formula first. So turns out that it's very interesting. So P of n is about 1 over 4n divided by square root 3 exponential pi square root of 2n divided by 3 as n becomes infinity. So as you can see, the right-hand side is clearly not necessarily an integer, right? It has transcendental numbers there and transcendental functions of those numbers, but it shows you like the behavior, right? So how quickly this sequence, as we sort of talked about in the previous table, what's the sort of growth rate of that sequence, right? So in order to obtain actual integer number, you need to write the whole series, which Ramanujan and Hardy at Cambridge sort of derived, and this is what the movie is about, right? You can make the sort of the answer more precise, but for large n, like maybe n at around 50, the formula works pretty well, right? So so if you like, the full formula is like this. So this P of n is equal to, so you need to take, so it's 1 over root 2 sum q goes from 1 to v square root q aq of n psi q of n. And here, so it's kind of a Fourier series. So it's an expansion of this harmonics sum of omega pq exponential to the negative 2 pi p I divided by q. So I is the imaginary unit here. So I squared is equal to -1. Okay, and then this one is the, so omega to the omega pq to the power 24 is equal to 1. It's one of the primitive 1 over 24th roots of unity. So you know you have a solution of z to some power n is equal to 1 in complex plane. It's not just z equals to 1, right? Because pretty much so if you have a complex number, which is over here on the unit circle with some angle alpha here, right? So if alpha is the fraction of 1 over 2 pi over n, right? So if you exponentiate it to the nth power, you'll get 1 again, right? So for 24, there'll be 24 points on the unit circle. There's 24 solutions of this equation, and this omega pq is one of those solutions. Okay. Okay, so this is the sum, and now the recipes that, and I haven't finished it here. So this now psi q of n, this function, it looks like this. It's the derivative d over dn of exponential pi over pi times this coefficient root 2 over 3 like multiplied by n minus 1 over 24. So 24 is not accidental. Maybe we'll talk about 24 later, divided by q. Okay, and now so what you need to do, you need to plug this everything into the series, and then you need to compute first several terms in V, but you don't need infinitely many. So in order, for example, in order to compute P of 200, which was, again, featured in the movie, you only need 5 terms. Need V equals 5 for P of 200. So we need V equals 4 for P of 100. So what's going on is that you write this formula down, you compute this several terms, and then you get a number which is not an integer. So for example, for 200, you'll get this. So the formula, so this formula here, let's say formula star. So star will give you 3. So the formula again from the clip, 999, 029, 388.004, right? And turns out that to get the answer, just drop the decimal part. So, and this will be the correct answer. Yeah. Now, that computation is much faster if you can than using the formula from with the using the than using this formula over here, right? So you can, I mean, in order to, I mean, of course, like you can set up an algorithm, but when n becomes large, you need to go pretty far, sufficiently far in the pentagonal numbers to use the recursion. However, here you just set up the series, and then you can calculate partitions of p of 1,000, p of 1 million, with just computing several terms of the series. Yeah. So in a sense, there is an algorithm of computing those numbers of partitions explicitly. So there's a p of n equals stuff, but you do need to investigate what value of what is the truncation number of the series, and you need to drop the decimal part. Questions? Oh yeah, and by the way, so we will sort of move into the second part of our program, in a couple of weeks. So you may submit me your you can think of what kind of stuff you want to study. Like if you're more into this analysis kind of thing, you can let me know. So I'll give you some problems with analysis. If you want to do the complex analysis stuff, is also fine. If you want to do something more combinatorial, also please let me know, and I can adjust your individual problems in that direction, right? So, or you want to do something completely different. So yeah, we can also take this into account. Okay, so you don't need to memorize this. Just make sure you kind of keep in mind this formula over here, so that the growth rate of the sequence p of n. So see, it goes as exponential to the square root n and divided by n, right? So it's it grows faster than any polynomial, but slower than any exponential, which is kind of rare, right? So it's a very special growth pattern. Well, you don't have to take notes. I'll send you the PDF of this slide together with the recording. It's better to just to follow. Okay. Good. Well, instead, let's prove something slightly simpler, which also show you the asymptotical behavior of the partition. So what we're actually going to prove is this theorem by due to Erdős and Lerner. So it says that as n goes to infinity, we'll talk about not p of n, but pk of n, right? The partitions with k parts. So pk of n behaves as 1 over n factorial, n minus 1, choose k minus 1. Where this symbol, I'm sure you know this, like n choose k is n factorial over n minus k factorial over k factorial. And also here it's assumed that k is this small o of n to the power 1/3. So in other words, k divided by n to the 1/3 goes to 0 as n goes to infinity, right? So so in other words, k is small compared to n to the 1/3. Right. So in this kind of range of numbers, this is the asymptotic behavior of the partition. And then you probably heard of the when n is large, there's a asymptotic presentation of a factorial. Have you heard of those? What's n factorial when n is large? Do you remember the formula? Like approximately how it looks like? It involves what? Some powers, exponentials, something like that, right? It's called the Stirling formula, right? Stirling formula. Well, we'll use it later today. So, which is sort of it's an asymptotic approximation of n factorial. So, anybody remembers this thing here? How does n factorial behave when n is large? Like n is 100, 1 million. Okay, it's fine. It's fine. We'll get to that. Okay. So let's prove the theorem. The proof will be sort of a little bit more combinatorial. Now, so for each partition of n with exactly k parts, we can associate the set of compositions of n made out of those parts, right? So we know that there are exactly k factorial compositions, right, of all parts into the partitions, which are distinct, right? So therefore, we can say that k factorial times pk of n is greater or equal than n choose k. Or we can write it as pk of n is greater or equal than 1 over n factorial times n times n choose k. Okay. Now, so that's sort of the upper bound. Actually, we can also put n minus 1, k minus 1 here. So you can check that this is even smaller than this. So it's kind of, so that would be the upper bound on this number pk of n. And then we show that the sort of, so the idea is the proof is also to show that pk of n is smaller or equal than this number plus something vanishing, plus something vanishing, plus something which is small. Okay. So let's try to constrain it from the other side. Now let's talk about the, distinct partitions. So say if qk of n is the number of distinct partitions. With all parts distinct, right? So and then yes, a number of distinct partitions of n, right, with k parts. So here's the lemma, which we can prove together. So pk of n, right, the number of all restricted partitions with k parts is equal to q k of n plus k minus 1 over 2. So all partitions with k parts, so that there's a one-to-one correspondence between the set of partitions of n with k parts, not necessarily distinct, and distinct partitions with k parts of this number. Can you suggest an idea why this should be true? Right, so remember, this is a triangular number, right? It's one of those triangular numbers. K minus 1 over 2. So how to make from a partition? So say you have a Young diagram, right? Of not necessarily distinct partitions. So say some of them are the same. So what do you need to do to convert it into a distinct partition? So you're allowed to add boxes, right? So say you want to add this many boxes, right? And then can you show me how to put those boxes on top so that the resultant partition will be distinct? So in this case, k is equal to 5, right?
You could use one of the boxes from the last column and then put it on the bottom.
Oh, no, you're not allowed to do that. So, I mean, you're not allowed to change the, so see, we fixed k. So it's the, we don't want to mingle with that. Yeah, so it's a different kind of transformation that we did before. So the answer is here, right? So you need to add this many blocks. So you need to put them on top. The question is where? So we don't want to change k. So k is it's the parameter that is fixed here. So what is k minus 1 here? So if k is equal to 5, then this is equal to 10, right? So we need to put 10 blocks to make the partition distinct.
Because the partitions can only like decrease or stay the same as they go, you can always add like 4 blocks to the first column, 3 blocks to the second, then 2, then 1, and you will always get a distinct partition because
exactly,
because it can only decrease.
Precisely, yeah. So in other words, so it's the so you have to so like sometimes it can be an overkill, but okay, let's do it again. So it's maybe a bit bigger. Did you understand what Kyle said? So he said that, well, you need to right. So Kyle said that so 10 is equal to 4 plus 3 plus 2 plus 1 plus 0, right? So then we put that many blocks in each of the columns. So we put 4 blocks here, 1, 2, 3, 4, 3 blocks here. So we put this staircase partition on top, right? And then because, well, these heights are all different, right? So 4, 3, 2, 1, right? And then the columns in the original partition were known to either decrease or stay the same, so they were not increasing. We are guaranteed that after we put those blocks on, all the heights will be different, right? Yes, that's exactly right. Is this part clear? So instead, the worst case scenario is that when the partition was all the parts were equal, right? So let's take this extreme example. Say take this partition here. Okay, so here, what is it? K is equal to 4, right? So then k minus 1 over 2 is equal to 6, right? So we need to put 6 blocks to make this partition distinct on top. Well, what's the most natural way to do it? Well, you just draw the staircase over here, right? Like this. And this is a distinct partition, precisely. You put 6 blocks on top. And then, as in the previous example, if the partition is not, is some of the parts are the same, some of the parts are not, well, it will still work, right? It is guaranteed to work. Okay. Is this clear? Good. Great. Okay. Now, next up, right? So that's done. So we can. So this formula allows you to interpolate between the all partitions and then distinct partitions. Okay. Now, but now we can use the same inequality we can write the same inequality like this for those distinct partitions, which is also true. So the k factorial, m it's a typo. There's no m. There's k. It's k factorial. So k factorial qk of n is less or equal than this n choose -1 k -1, or because of this formula here, because of this lemma, right? We can say that pk of n, right, is equal to qk of n plus k -1 over 2, right? It's less or equal than 1 over k factorial. And then here it will be n plus k -1 over 2 minus 1 k -1. Okay, so that's so this is not a bound, right? And now, well, we need to combine this inequality with this inequality here. So we know that it's sort of this value is squeezed between. So we know that pk of n is greater or equal than 1 over k factorial n minus 1 choose k -1, and it's greater or equal than well, this thing, which you can write as, well, yeah, yes, it's 1 over k factorial n plus k -1 over 2 minus 1 k -1. And now let's divide by the left-hand side. So we're going to divide by this, and we're going to estimate the right-hand side. So 1 is less or equal than pk of n over right, and on the right we'll have just using the definition of the combinatorial coefficient, we get n plus k -1 over 2 minus 1 factorial times n minus k factorial divided by n minus 1 factorial, and here's n plus k -1. Actually, because of myself, we can write this k -3, right? So k -3 over 2 everything factorial. Okay, and now, well, this is the, so at this point we will use this approximation, the power approximation of asymptotic presentation of the factorial. So asymptotically, we can present the right hand side as is equal to yeah, so so first of all, it's equal to well, we introduce this function here. I'm going to write this as introducing gamma function. So there's a gamma function, which is another function which is used in complex analysis. But what you need to know is that this gamma function of an integer, so gamma of n is equal to n minus 1 factorial when n is an integer. If n is not integer, this gamma function takes different values. So it can be represented as a certain integral, and we'll talk about this in a second. So I'm going to rewrite this as gamma function. So it's gamma of n minus k plus 1. It's from the second part times gamma n plus k minus 1 over 2. Right, minus 1 got eaten, and here it's gamma of n and gamma of n plus k minus 3 over 2 plus 1. Okay, and now we'll use this Stirling formula for the approximation of n. So let's prove the formula later. So using Stirling formula for gamma functions. So this can be represented as, so that this is approximately equal to n to the power minus k plus 1. And this is approximately equal to n plus k minus 1 over 2 to the power k minus 1. And here it's provided that that k is the small o of n to the 1/2. So if k goes to 0, if k divided by n goes to 0, by n to the 1/2 goes to 0 and goes to infinity, then this is true. So let me finish the proof. We'll get to this formula in a second. But assuming that this is true, right? So claim that those factorials, those gamma functions at large n and k, provided that this formula holds, they behave like this, right? Then we can continue. So this is equal to 1 plus k minus 1 over 2 n to the power k minus 1, right? You can just divide by n here, right? And this you can write as the exponential, right? So it's exponential of k minus 1 logarithm of 1 plus k minus 1 over 2n, like this. Or here, so remember n is large, right? So we're assuming so n is large, but k is not very large, right? So we can now use the Taylor expansion for the log. So do you remember what is it? What is log of 1 plus small number in the first approximation? So what is from calculus? Do you know this? What is say log of 1 plus x, where x is small, approximately? So you probably know that e to the x is approximately 1 plus x when x is small, right? What about log? There are other corrections, right? But then here, what's the one with the logarithm? Is it 1 plus x or is it 1 minus x? So you can sort of try to draw it, right? So so not one, it just x or plus, right? So see, log looks like this, right? Log x, and then
I think it is x.
It's x, that's right. So it's approximately x, and then then signs alternate. Yeah, so right. So this is x. So the whole thing approximately equal to exponential, and then you just x is this, right? So you just multiply it here. So it will be equal to k minus 1 squared, right? Because there's another k minus 1 divided by 2n plus corrections. Right? So if you replace log 1 plus x with x, where x is this fraction here, you just multiply it by k minus 1. Okay. Eunice, is this clear? You look a bit puzzled. Okay, good. And then, well, so this thing, so if this conditions of the theorem are satisfied, right? So if you say that, so if k cube of n goes to 0 as n goes to infinity, then the whole thing goes to 1, right? So the exponent, so this fraction goes to 0, and then the exponential is equal to 1. And then if you recall where we started, right? So remember we squeezed it. So the exponential was the estimate for this part. So the thing is, this fraction pk divided by this factorials is squeezed between 1 and 1, right? So therefore, this has to be asymptotically. This also has to be equal to 1. So that the theorem follows. Okay, so we haven't proven this formula yet, but we'll do it right now. Any questions otherwise? So it was so the estimate was based on this this inequality here, right? So that the number of partitions with k parts, right, multiplied by k factorial, right? So it's sort of the number of permutations you can make of, permute them around. So ck, that should be greater or equal than n choose n minus one choose k minus one. And here, but with the distinct partitions, sort of the inequality goes the other way around. So kind of we had these two different boundaries from where we can squeeze the function. So this pk of n was squeezed between this value and between that value, right? Sort of we use this lem over here. So this lem was crucial, so we can sort of the way distinct partitions work and the way the all partitions they work is a bit different, but there is a relationship between them. So we could use this to our advantage. Okay, now let's talk about this gamma function. So that's sort of a, let me know if you need more explanation here. Sort of. So sort of fully complete the proof, we need to show that this is true. So gamma function. Right, it's a sort of important part of this. So you should think of gamma function as this analytic continuation of the factorial function, right? So we define it like this: so gamma of z is equal to integral from 0 to infinity x to the power z minus 1 e to the minus x dx. And here it's assumed that the real part of z is greater than 0. So you know what the integral is, right? So what is the definite integral, how to integrate functions and stuff, right? Good. So yeah. So here it's you integrate over x, real variable, right? And z is the power over here. So it's a function with many interesting properties, but for today we'll need this asymptotic approximation here. I think is so. Yeah. Now I'm going to give you a very sort of quick estimate of how the asymptotic look like. It won't be as precise as it could get if you do it very carefully, but at least we'll get the idea where it's coming from. Now let's rewrite this integral slightly differently. So I'm going to rewrite it as I'm going to put this x into the exponential. So you have integral from 0 to infinity e to the minus x plus z minus 1 log x dx. And so I just put it upstairs, and let's call this expression over here s of x. So it's some function of x. And so s of x is equal to minus x plus z minus 1 log x. And now I'm going to do, we'll find the extremum of x. We'll take its derivative and then put it to 0. So this way we'll find the, so first, so the idea is the same as with the derivative of a function. So the function has a minimum or a maximum if the first derivative vanishes, right? So, if you have a function of one variable, then if its derivative, it's the tangent, it has the slope to the tangent line to the graph. And if it's horizontal, the derivative is vanished, derivative is equal to 0. And that tells you that the function has a maximum or the function has a minimum. So we'll use this idea, the same idea to this function nulls, right? So you should think of this as a map from space of functions, these functions to numbers, right? Which takes values in complex plane here. So we'll try to find the extrema of this functional. Okay, so let's do it. So s prime of x, let's just take the derivative, is equal to -1 plus z minus 1. What's the derivative of the logarithm? What's log x derivative? It's a natural log with the base e. So when I write log, I mean log base e.
In that case, it would just be 1 over x.
Yeah, that's right. It's 1 over x, right? So it's over here. So you can derive it using the property of the derivative of the inverse function, right? So y is equal e to the x, and derivative of if e to the x is the function itself, and then you express, find x is a function of y, and you'll sort of you can derive that. Okay, so s prime of x is equal to -1 plus z minus 1 over x, right? And then you want to solve equation s prime of x is equal to 0, and find this kind of the location of this extremum of this critical point, right? So let's solve this. What's the solution of this equation? Kind of solve -1 plus z minus 1 over x is equal to 0. Right, so x is equal to 1 over z minus 1, right? Oh, sorry, just z minus 1. Yeah, x is equal to z minus 1. Right. So if x is equal to z minus 1, everything is cancelled. You get 0. So let's call it x star. Right. It's the kind of the position where this extremum happens. Right. And now let's calculate the value of s at this extremum. So s of x star, right, is equal to 1 minus 1 minus z plus z minus 1 log z minus 1. And if you evaluate this exponential e of s to the x, you'll get e to the 1 minus z, which is a constant. Yes, e to the minus z times z minus 1 to the power z minus 1. Now, there's a theorem in analysis which shows you that sort of the asymptotic behavior. So if this is so you can now kind of study what happens to this function as x deviates from this x star position. So when x is equal to x star, then this function is equal to, like, the value of this integral will be will be given, sort of the main contribution to this integral will come from this is called saddle point, also saddle point approximation. Right, so from the saddle point, you get this, so that this gamma of z approximately will be equal to this thing. So it goes as e to the minus z, right, times this z minus 1 to the power z minus 1. So that's how this power appears. Yeah. So I skipped over a couple of things here, but so first of all, so we need to kind of argue that this approach kind of makes sense, but you can think of it as this asymptotic kind of finding the stationary point, right? So find the critical point where the derivative of this functional is equal to 0, and then using the value of this s of this function s evaluated at the position of the critical point, and that gives you the approximation for the value of the function itself. So it turns out that this is the value. Now, if you do it a little bit more precisely, right, you can get more precise formula. So the actual Stirling formula works like this, which it goes a little bit beyond the scope of the course, but it would work like so gamma of z is approximately square root of 2 pi z minus 1. So you cannot get square root from here. And then times z minus 1 divided by e to the power z minus 1. So there is some coefficient here which you cannot determine by this asymptotic behavior, and this coefficient may depend on the argument slowly. So this square root thing you cannot find, but you can capture precisely the this power dependence. And that's exactly why we use this formula here. So that's why sort of this ratio is equal to this thing, and then this ratio is equal to that thing. So that allows us to do this cancellation. Because these functions behave exactly in the same, behave exactly in this way. Okay, questions? Good. So I'll leave you with the notes, and then yeah. So let me know next time if you have questions about this direction. So again, let's recap what we did. So we have proven the asymptotic behavior of the restricted partition of n with k parts, right? And then it behaves like this, right? So that's the approximate value for this formula here. Okay. Oh, it's actually, there's a typo, there's a k factorial. I apologize. Otherwise, this is less than 1. K factorial. So if you write it down, it will be what is it? N minus 1 factorial over k factorial, k minus 1 factorial, n minus k plus 1 factorial. And again, you can use gamma functions to approximate it even further. So there'll be some kind of exponential behavior in those partitions as well. Okay. Good. And the last story for today, I need to give you a couple of problems with the partition functions. So I'll give you some second, let me scroll it back. So here. And next time we'll talk more about partition functions. Okay, so another theorem. So if absolute value of q is less than 1 and absolute value of t is less than 1, then 1 plus infinite sum n goes from 1 to infinity, 1 minus a, 1 minus a times q, 1 minus a times q squared, and so on, 1 minus a q to the n minus 1, t to the n. So it's a power series in t to the n with those coefficients, right? So it's right here. So t to the n divided by 1 minus q, 1 minus q squared, and so on, 1 minus q to the n is equal to product 1 minus a t q to the n divided by 1 minus t q to the n. Product n goes from 0 to infinity. Right. So what it says here is let's first try to understand what the formula is doing. So on the left, we have a series in T with these coefficients. So coefficients are rational functions in A and Q. And on the right, you have infinite product of this rational functions. So expressions, they look completely different. Yeah, so it may look a bit scary, but let me kind of give you a little motivation here. So where does this formula come from? So it comes from something that you know very well. Let's say you take you calculate 1 minus t to power say to power yeah, so see, good, right? So say you have 1 minus t to the power n. What is it equal to? So say n is an integer, right? And then, well, you just want to compute this expansion. So you multiply the parentheses, right? And you'll get this coefficient, right? So you have 1, well, you have the sum of binomial coefficients, right? You have sum of n choose k, right? T to the k. K goes from 0 to n, right? And these are the binomial coefficients. So if n is an integer, we'll have n plus 1 terms. We'll have 1 plus nt plus its next coefficient, n choose 2 t squared, and so on and so forth. So well, these coefficients, you can calculate them from Pascal triangle. Now, what if n is not an integer? So what if n is not an integer? How will this formula change?
So you're asking if like n is a complex number?
Say for now, let's say it's real number. Yeah, but, although with the complexes, it wouldn't make any difference. So say it's a real number, but it's not integer.
Okay.
But yeah, if you like it, I mean, it doesn't really matter. So what matters is that it's not an integer. And then also let's assume that it's yeah, it doesn't really matter. Yeah, sort of. So yeah, because the idea is to write. So to write this expression 1 minus t. So let's denote it alpha. So it will be less confusing. So alpha is not an integer, right? And we want to write it down as a sum of terms in powers of t. Yeah, so if you did the Taylor series in AP calculus, you would have known. So do you remember this, or maybe it was not covered? Did you study Taylor formula? Taylor series? No, okay, it's fine. Yeah, sort of. We won't be using it too much, but yeah. So what I asked you before, so for example, the fact that e to the x is approximately 1 plus x and plus x squared over 2, or sine x is what? X. Do you remember what's the next term? When x is small, how does sine behaves?
So minus
Yes,
x cubed
over
divided by the factorial of 3.
by 3 factorial. That's right. Yeah. So you'll get factorial, and then yeah, with the exponential, it's x to the power k over k factorial. With sines, these are also factorials, but of odd numbers, right? And with cosines are factorials, but even numbers, and they alternate. Now you can do the same formula for this. So it's equal to 1 minus alpha t, right? So maybe I can put let's put plus here. I think plus would be easier. Yeah, so plus, because here you need to do -1 to the k also, right? K plus 1. 1 plus alpha t, and then it's plus alpha minus 1 over 2 t squared plus alpha minus 1 alpha minus 2 1 times 2 t cubed, and so on, right? So if you look at those coefficients, you should recognize exactly the binomial coefficients, right? Because see, what is n factorial? What is the binomial coefficient n choose k, right? So n choose k, right, is n factorial over k factorial over n minus k factorial, or it's it's the k factorial times k plus 1. Oh, sorry, let's do it backwards. It's n times n minus 1 times n minus 2, etc., times n minus k plus 1 times k factorial. So with single out n minus k terms first, divided by k factorial n minus k factorial. So k factorial cancels, right? And you'll get you'll get this formula, right? So now, so you have this power here, and then this alpha minus 1, alpha minus 2, and so on. So the only difference with this series, with the binomial expansion, is that here the series truncates, because at some point it'll hit n minus n, and the whole thing will be 0. But when this alpha power is fractional, the series will go forever. Yes, Emily, what's the question?
For a Taylor series, doesn't it depend on where it is centered as well?
Yeah. So here, sure, absolutely. So here it's assumed that it's around x equals 0. Yeah.
Okay, so it'd be like a Maclaurin series.
Yeah, that's right. Yeah.
Thank you.
So here it's t equals 0. Good. So there's a sort of serious generalization of this binomial coefficient formula. And the claim is that the formula that I wrote for you in green is a sort of another generalization of this formula, only instead of binomial coefficients, you have this, well, two-parameter generalization. Like there's a rational function, instead of just a number, you have a rational function which depends on two parameters, q and t. So the right-hand side is some product, like here, right? And the left-hand side is a series, like there. Yeah. So this is called the Cauchy formula. Well, there are many Cauchy formulas. It's one of them. Yeah. So we'll prove it. Well, I guess already next time, and then using this formula, we'll prove some corollaries. So this will be the homework. So I think now we're running out of time because I have to go to another meeting. So I'll make the separate PDF with the homework. I'll post it on the website. So there'll be a homework to prove a couple of identities using this Cauchy identity. So claim that this is an identity. It happens it's true for all values of a, q, and t, provided that these things happen. Yeah. So we'll do this, and next time we'll apply it to theory of partitions. Okay. Good. Awesome. Thank you guys. I'll see you next week. Thanks. Bye.
Thank you so much.
Thank you. Bye.
Thank you. Bye.
Thank you.
Goodbye.